Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the normal distribution. In particular, we'll look at solving probability problems using z-scores. So the normal distribution is easily the most important probability distribution in statistics. Firstly, because a lot of real-world phenomenon either follow a normal distribution or are closely approximated by a normal distribution. For example, IQ scores. But secondly, there's something called the central limit theorem that really highlights the importance of this distribution. Now, we're not going to go through the central limit theorem in this course, but just to give you an example, we looked at Bernoulli trials last semester. So they were, experiments where there were two outcomes. It turns out if you keep performing Bernoulli trials over and over again, the number of successes follows a normal distribution. The graph of the number of successes and its probability will look like this. So these are the shapes of a normal distribution. They're always bell-shaped, so they might be a bit fatter like this or a bit thinner like this. It depends on the variance of the distribution. I just want to make a quick note. A lot of people, when they say bell curve, they mean the normal distribution, but that's not the proper name because there are other distributions that are bell-curved. But normal distributions are always bell-shaped. They're always symmetrical, and they're symmetric about mu. We know that mu is the mean or the expected value. So mu is right here in the middle. It turns out mu is the mean, median, and mode. All of these three things are equal to mu when we're talking about a normal distribution. So when a random variable x is normally distributed, we write it like this. This says x follows a normal distribution. Its parameters are mu, which is the mean, and sigma squared, which is the variance. So make sure you take note of this, that this number that goes in here is the variance, because pretty much every calculation involving the normal distribution, we will use just sigma by itself, which is the standard deviation. So this is the PDF of the normal distribution. Because it's a PDF, the area under this curve is always equal to 1. So in this formula, we see mu, which as I said means the mean or expected value, and there's also sigma, which means the standard deviation. Sigma, standard deviation, sigma squared is the variance. So this is quite a complicated function. In fact, it's so complicated, we couldn't integrate this by hand. If we wanted to use this PDF to find probabilities, we need to use numerical methods for integration. Now, fortunately, someone has already done that. It turns out for any normal distribution, whether it's like a bit fatter or a bit taller, these rules are always true. There's always 34.13% of scores between mu minus sigma and mu, and there's 34.13% of scores between mu and mu plus sigma. What does this all mean? So this means one standard deviation below the mean. This is one standard deviation above the mean. So adding these two numbers, we get 68.26% of scores lie within -1 and 1 standard deviation of the mean. 68.2% of scores are between 1 standard deviation below the mean and 1 standard deviation above the mean. That is true for any normal distribution, regardless of what the mean and variance are. Similarly, over here we have 2 standard deviations below the mean. That's what 2 sigma means, 2 standard deviations. And over here, 2 standard deviations above the mean. If we add up all these numbers here, we get 95.44% of scores lie within -2 and 2 standard deviations of the mean. So 2 standard deviations means 2 above the mean, -2 standard deviations means 2 standard deviations below the mean. And similarly, for 3 standard deviations below the mean, 3 standard deviations above the mean, adding up all those numbers, 99.72% of scores lie between -3 and 3 standard deviations. So how is this going to help us with probability calculations? Well, what we're going to do with all of our probability calculations, we're going to get a score. We're going to find how many standard deviations it is above or below the mean, and then calculate the probability of being that many standard deviations from the mean. So to do this, I'm going to introduce the standard normal distribution, which is called Z for some reason. That's a normal distribution where the mean is 0 and the standard deviation and variance are both equal to 1. So if this was a standard normal distribution, mu would be 0 and it would go 1, 2, 3, minus 1, minus 2, minus 3. So why do we need the standard normal distribution? Well, back in the day, calculators couldn't calculate probabilities from a normal distribution, so people relied on tables, these big sheets of paper with a list of probabilities. The problem is you couldn't come up with a table for every possible mean and variance of a normal distribution. There are infinitely many. So what people did is they just made a table for the standard normal distribution with mean 0 and variance 1. See, it turns out that it's really easy to convert a score from any normal distribution to a score from the Z distribution. And I'm now going to show you that on the next slide. So the idea here is simple. We have a random variable that's normally distributed with mean mu and variance sigma squared. What we do is we take a score, so little x is a score from this distribution, and we put it into this formula. Score minus the mean over the standard deviation. What this tells you is how many standard deviations your score is above or below the mean. What you're actually doing is you're transforming. You're taking a score from a normal distribution and you're changing it so that it's from the standard normal distribution. So remember, standard normal distribution is mean 0, variance 1. So here's our example. So we have scores from a normal distribution with mean 75 and variance 16. So note the variance is 16, which means the standard deviation is the square root of 16, which is 4. So I'm going to convert this score here to a Z score. So it's score minus the mean divided by the standard deviation. So if you put that on your calculator, you just get 2. So this number 2 is saying that this score is 2 standard deviations above the mean. That makes sense. Mean 75, standard deviation 4, 79 would be 1 standard deviation above, 83 is 2 standard deviations above, 87 is 3 standard deviations above, and so on. And this is exactly how we calculate your Z scores when we're talking about from tests. So if you got a Z score of 2, it means your score in the test is 2 standard deviations above the mean. So what about if X was 69? We're just going to use the same formula. Score minus mean divided by standard deviation. So if you put that on your calculator, you get minus 1.5. So that means that this score was 1.5 standard deviations below the mean of 75. So of course our Z scores don't need to be a whole number, and because our original scores came from a normal distribution, these scores here will be from the standard normal distribution, which means mean 0, variance 1. All right, let's see how we can actually use this to solve problems in probability. So here's how we can use Z scores and the normal distribution to solve problems. So I told you before, IQ scores are normally distributed. Turns out the mean and variance of IQ scores are both equal to 100. So if I randomly select 200 students from Marist, how many would we expect to have an IQ above 120? So this is how we approach problems involving the normal distribution. We're going to convert 120 to a Z score. So it's 120 score minus mean divided by the standard deviation. So if the variance is 100, as the question told us, then that means the standard deviation is the square root of 100, or 10. So that is 2. So if you have an IQ of 120, you have a z-score of 2. That is 2 standard deviations above the mean. So from the diagram on the very first slide of this video, it's also on the question sheets, we know that 95.44% of scores lie within 2 standard deviations from the mean. So what about the other 4.56%? Well, you'd have half of that here, so you'd have 2.28% here, and you would have 2.28% here. So what that means is only 2.28% of scores from a normal distribution are greater than 2 standard deviations from the mean. So the probability you get a z-score that's more than 2 is only 2.28%. So that means of these 200 people, we expect only 2.28% of them would have an IQ above 120, which is 2 standard deviations above the mean. And of course, 2.28% of 200 is 4.56, or we'd round it up to about 5 students. So how many would we expect to have an IQ between 80 and 110? Well, let's convert these scores, 80 and 110, to z-scores. So a score of 80 minus mean divided by standard deviation is minus 2. An IQ of 80 is 2 standard deviations below the mean. An IQ of 110 is 1 standard deviation above the mean. So this question is really asking what percentage of students would have a z-score between -2 and +1. So from the diagram on the first slide, the one that's in the question sheets, we know that the probability of having a z-score between -2 and 1, there's 13.59% of scores here between -2 and 1, and 68.26% of scores are always between -1 and 1 standard deviation from the mean. That works for any normal distribution. So just adding these two numbers together, we get about 81.85% of students would be in this area from -2 to 1 standard deviations from the mean. So of course, 81.85% of 200, you just times 0.8185 by 200. So the answer you get is 163.7. We'll just round it up. So it's about 164 students. So whenever you're solving probability problems involving the normal distribution, you'll always be finding the probability you get a score within a range. So what you do is you convert the scores of the range to z-scores. You find out how many standard deviations they are above or below the mean, and then you can use the probabilities that have already been calculated from the standard normal distribution. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.